Give me one second. Okay, so my apologies. I'm going to switch back to the careers and tech screen here for just a minute. Okay, so we're doing the Careers in Tech Summer Series with our speaker, David Fisher. And we're going to go ahead and start the recording, which we have done. And without further ado, I'm going to switch it back over to our speaker for the night.
Okay.
All right, so the numbers are continuing to climb. We're past 50 now. So I think we've got it.
Can you see the screen now?
We're still seeing your video right now.
Okay, so all we need to do is figure out how to.
Yeah, at the very bottom of your screen, there should be a share screen option.
Yes, there we go again.
And to answer your earlier question, I'm personally based in Northwest Florida, but we do have people from all over the country here. And I believe possibly some people even up into Canada.
Okay. And where are you located?
So I'm located in near Pensacola, Florida.
Okay.
But I opened it up to region 1 through 7. Apparently tonight we actually have someone in Australia.
Ah, interesting. Yes.
Well,
okay. Well,
you've got a worldwide audience tonight.
Yes. Okay. Well, I think it's the first time I've given this lecture in the United States, actually. Seem to get more requests from Canada than the US. Okay, so can you see the slide now?
Yep.
Okay, good.
Along with part of your background on that screen, but that's fine.
Along with what?
Along with the desktop for that particular screen. Okay. I think that's probably about as big of the keynote screen as you want to go, because much larger than that, you'll lose the bottom.
Okay, so you're okay with it now?
Yeah, I think we should be good.
Okay, good. So I was asked to talk about why software fails and why AI can't help. The abstract scenery. And basically, I'm going to try to talk about four things. First off, software development and its problems. Secondly, what artificial intelligence is and is not. And if we have time, human deductive reasoning, and then in my own current project that relates to this. So software. Well, software development is difficult. And some of the reasons are that this is probably ideas from the 1960s, exponential advances in speed and capacity and reliability of digital computers have not only opened vast new applications, but they've also created exponential growth in expectations for software and exponential growth in the complexity of software. And so the expectations that software were going to improve as much as hardware really have not been achieved. If you look at the size of any program today compared to what it was 20, 30, 50 years ago, regardless of its functionality, it's gone up in size. And often down in significantly in speed relative to the underlying hardware. And then software development is labor intensive, which gives a hint about how you might fix that problem. And then, of course, software is viewed as malleable, while hardware is viewed as immalleable. So any kind of evolution in system requirements or bug fixes or system problems, even hardware problems, often get repaired in software. No, I'm not.
They're not advancing.
I'm not advancing. Right. So.
Oh, there you go. No. Okay.
Okay. Yes. So what's some evidence? Well, most large software is never fielded for its intended purposes. And I'm guessing that most of your audience knows that, but basically, if you look at large software systems over the last 30 years at least, most of them never actually get fielded. Most of them not at all, and if they're fielded for purposes other than their original intent. And it's because the functionality doesn't satisfy the requirements, the performance is too slow to be practical, and often there's just the resource consumption makes them not cost effective. And part of it is that no one really understands fully any software system. And bugs are pervasive in software. Nobody believes you're going to have bug-free software. Although one might ask, why is that? And finally, there's the general problem that's certainly understood by the Microsofts of the world, which says that once you have a system that's actually operational and lots of bugs are discovered, that there's really no way to reduce the number of bugs. You can fix any given bug, but on the average, the number of new bugs that are created by fixes is equal to the number that you corrected. And in fact, a lot of companies, those companies that build large-scale software, have internal policies that says never fix a bug until you get significant numbers of complaints about it from your users. And that applies not only to any bug, but to security bugs as well. Okay, so what's the state of the art? So we had 70 years into software development at least, and software is still unreliable. It's not comprehensible to its users and authors, and it's still handcrafted. We really don't synthesize any software from requirements. Okay, so and then there's the basic problem, and certainly from 1960 on, the pervasive view in the software community was that in the same sense that the Industrial Revolution really amplified human physical abilities, that software and computers would amplify human reasoning abilities. And it just hasn't happened. And in fact, despite the many applications, computers basically are still only used for the four particular purposes, namely record keeping and retrieval tasks, numeric computation, real-time process control, and modeling and simulation. And as an aside, modeling and simulation on computers is inherently inaccurate. And one might say, well, where's AI in here? And the answer is, it's on my list. Because I don't think we're really making effective use of AI. So let me move on to AI and AI/ML. And by the way, if there's a mechanism here, I'm willing to take questions as I go along, but I certainly will answer about any of these when we're done. Okay, so what's the purpose of AI? Well, the answer is I don't know. It's never clearly stated that I can find. But perhaps it's to emulate or replace humans. That seems to be consistent with the statements that AI practitioners make. And I don't know why we would even want to do that. So here's some quotes. 1956, John McCarthy, the person who coined the term artificial intelligence. Every aspect of learning or any other feature of intelligence can in principle be, I can't even read my own. Let me get rid of this.
Be described. No.
There we go.
Make it slightly small.
Okay, so it can be described so precisely that a machine can be made to simulate it. Well, first off, that's just not true. We cannot precisely define anything or explain everything. In fact, a precise description of most things, certainly physical things, requires an uncountable number of specifications. And then there's just practical aspects of this. It's not practical to describe anything in minute detail. And then finally, there's the argument that, well, physics is actually emergent, and so it's non-reductionist. In any case, it hasn't proven true in practice. Then Malvin Minsky, yes, in 1970, he said, well, 3 to 8 years we'll have machines of general intelligence for the average human being. The answer is probably not. I was around in 1978 and I didn't see that. Then machines will surpass human cognitive abilities in all tasks, including abstract thinking and self-recognition. That's a new statement that came out of Harvard. But I'm skeptical. Can I have a sheet? Okay, so here's some ancient examples of, well, some older examples of AIs. And they go way back, 800 BC. Talon, which was a 30-foot bronze statue, was brought to life by the guy that forged it. And maybe that's true and maybe it's not, but I'm skeptical. I'm going to keep saying that. 1500, Pericles. This is the most famous doctor in Europe at the time, father of toxicology. And he created an artificial man out of magnetism and sperm and alchemy. And I don't think anybody's challenged that, but I'm still doubt that it's true. Then there was the mechanical Turk, and there's so much evidence of this that it basically paid master level chess for some number of years, which I forget, and it's on the screen.
97.
97, okay. Yeah, and it played master level chess all over the world. And that's a picture of it in the right hand corner there. It's probably 4 foot high mechanical chess player. It also turns out in that case that after it was destroyed by a fire, the owner of it revealed that actually they always had master chess players that were very small inside it. Okay, and in the more modern world, Joe Weissenbaum created Eliza. Eliza was an automated psychiatrist, basically. And probably a forerunner to the chat bots of today. And probably, except for the large database, about as successful. It basically fed people's statements back to them in the form of questions. And then Terry Winograd, he produced a natural language understanding microworld, 1968. And by 72, he announced that, well, actually, it was a dead end. And Doug Lennott, he had this enormous project to build computers with common sense. And I'm not sure what happened to it after 1995. But I don't think we see it out there being used. And some more examples. 1980, Ed Feigenbaum, who the last time I saw him was at Stanford, invented expert systems. And supposedly they could solve any type of complex problem as long as it was limited to a particular domain, and easily understood by its users, and takes input from human language and effectively generates accurate and accurate output, and provides high performance response to complex queries within a short period of time. Well, that's all a nice claim, but again, and there were hundreds of millions of dollars spent on expert systems in the 1980s, but we really don't have any effective expert systems in use today. And then there's newer systems like Chat GPT and chatbots in general. Which basically take in large quantities of text from any available source and generate great sounding text. And they really are, it is very great sounding text. It does a good job at that. But there's no semblance of common sense to it. There's no real world understanding. And it just produces, bizarre results. And then I don't know how many of you know of the system called Sophia, but it's basically a chat box with a nice looking woman's head on it and arms, and I don't think it has any legs. And it actually has been going around and appearing at conferences and giving lectures on business and science, and was actually recently given Saudi Arabian citizenship. So it's probably the first AI with national citizenship anywhere. Okay, so with those examples, here's some views from AI experts. Some of them are pro and some of them are con, but they're people who purport to be experts in this. John McCarthy, and this is way back. Well, I said that before. I won't read you that again. No, I apologize. I have duplicative points here. Okay, large language models are good at saying what answers should sound like, but not what the answers, what are the correct answers. And then there's the Watson and other systems. Watson in particular was a really big investment. I guess I think that was the one that was. Yeah, I apologize. I can't see the whole screen myself.
Yeah. Oh.
Yeah. Sorry. Okay, I'm going to try that. Okay. Okay, so Watson, yeah, really big investment, but it showed that it could win at Jeopardy, and other AI systems, they're deep learning based, have played in one. They've beaten the world chess champion. They've beat the world Go champion, who in fact gave up Go because he felt it was better than he was. So lots of evidence of capable systems. Oh yes, and so Sophia, it's a product of Hanson Robotics, and they claim that it's basically alive. And for a different opinion on that, the director of artificial intelligence at Facebook says it's really a bunch of junk. But it has the typical, I would say, lower grade chat box capabilities. Then there was a statement actually in the IEEE Spectrum for July of this year. Number of articles in AI, but one point that was made was that rogue AIs are really human errors of their designers and trainers. And I guess I'm bothered by that, because you can't have it both ways. Either the AIs are demonstrating intelligence, and their errors are their own, or they're not. And then there was a statement which is kind of humorous. I don't know what was intended by it, but artificial intelligence is probably not out to destroy all humans. I happen to believe that because it's I fear AI, not because it is likely to meet its intended purposes, but because it won't, and people believe it will. Okay, so just to emphasize these points, what we can observe is that expert systems have not replaced experts. that natural language systems do not understand natural language. Game playing programs lack strategic ability, and although they can rival humans in particular game context, but not by human methods. And by the way, for chess and Jeopardy type games, there's belief that they can't repeat that those wins. And part of it is because they don't play the way humans play, and the game players are used to playing with humans. And so they really have to learn a new approach if they're going to be able to consistently win as humans. And then the best chat programs have no idea what they're talking about. It's just statistical analysis. And someone recently said that, you know, AIs do not understand, they do not realize or teach themselves. They know only statistical representations of the world, and only then is depicted by their training data. And actually, this came from one of the articles in Spectrum again in July. And they were really proposing this as a test when people are making claims about AI. How do you know if they're exaggerating? And if they're claiming understanding, if they're claiming that their AI realized something or taught itself something, it's probably an exaggeration. And then there's this thing about, you know, AIs are really intended for situations of uncertainty. But, you know, probabilistic estimates really they don't proclamate judgment under uncertainty for humans. It's, if you think about it a bit, it's let's say at least rare that when you make a decision that you do it based on probabilistic estimates. And you might ask yourself, would you want to ride in an automated car that's making probabilistic judgments based on data that it's seen other people doing? And it's not the way humans drive cars. Humans drive cars based on norms, which are probably based on probabilistic estimates of normal conditions. But what humans do when there's a unusual situation, they don't depend on that probabilistic estimates anymore. They switch to a deductive reasoning to deal with the unexpected situation, and we just don't have that in AIs. And then chatbots don't have an underlying model of the world or connection to the world. And this was some numbers on this. So what happened was that Microsoft invested $10 billion in ChatGPT, and it's now the product of a company called OpenAI, which apparently is currently valued at $30 billion. I tend to invest in high-tech companies that are young and I have a lot of confidence in, but I wouldn't invest in that one. Okay, so my summary for AI is that AI efforts have been extremely expensive demonstrations. Their results have not been cost effective. Results do not generalize or scale. And when I say this, I'm not talking about some AIs. I'm talking about basically all of the big investments in new AI technology are in this category. But of course, you know, the new technologies of the day, the ones that have not yet been abandoned, are ML and large language models. And so, of course, unlike all their predecessor, things will be different in this case. Okay, so we get a lot of expensive artifacts, but we don't get long-term value. Okay, so let's go back and look at the maybe the bigger picture on this, and in particular, what is human intelligence? And so I thought I would list here just some things that humans do that AIs can't do. AIs can't do sound deductive reasoning. They can't do math and science and engineering. AIs, and in fact, even most formal logics really don't do abstraction and generalization and analogy. On the other hand, those are three operations that are, well, at least abstraction, generalization, and specialization are primitive operations in human deductive reasoning. AIs don't recognize inconsistencies. In fact, they don't. They're happy with inconsistencies. Inconsistencies are just more data. Where in deductive reasoning, inconsistencies are enable proving false, as proving that false is true. AIs don't distinguish things from their representations. That's what in logic's called intentional. The things in the representations be distinguished, although we often don't. Both computers and AIs can't reason sound, well, AIs can't reason sound about anything. Computers can't reason soundly about things that are that cannot be completely represented. That was the point earlier about simulations are always inaccurate because we often try to represent. We often try to simulate things that we cannot fully represent, at least not accurately. I guess to make that point, any physical thing cannot be both accurately and completely represented, period. If you had a model of a physical thing that's both accurate and complete, the only possible model would be the thing itself. And that's for physical things. For abstract things, mathematical objects, you can have a model of it that's accurate and complete, providing it's finite, or even countable for that matter. But if it's got an uncountable number of properties, then it's not representable, even if it's a mathematical object. And so we end up with this small set of simple mathematical objects are the only things that we can do accurate computation with. Okay, big criticism of AI has been that they can't explain their results. Well, it turns out that logics are very good at explaining their results. Computers are not able to explain their results, but in theory, they could be analyzed and explain their results at least. AIs, particularly, and when I'm talking AIs here, I'm talking machine learning methods just preclude that explanation. Then there's the issue of performance. Most logics and certainly AI learning algorithms require time that's proportional to, that's n squared in some measure of their size. And n squared computations are just not scalable. You need something that is strictly less than n squared. And humans, on the other hand, are quite good at doing complex computations in less than n squared time, which I call near linear, but I really mean by that less than n squared. I'm always amazed that even with the largest computers, I often meet grad students who've done some great simulation. Some great formal proof program, and they're able to accomplish something in only a few hours that might have taken weeks, a few years ago. But on the other hand, if you take that same problem and you give it to a human who knows logic, they can do it in a few minutes. So we are not getting anything resembling human reasoning capabilities out of machines or AIs. And finally, there's a number of things that are often associated specifically with AIs, namely ability human AIs do not have these capabilities, but human deductive reasoning does, namely understanding of concepts, understanding of language, self-awareness. Large language models and natural language processing, neither one demonstrate language understanding and self-awareness. Okay, so then there's this separate point, which I haven't heard elsewhere, but it strikes me as maybe as the real point about AIs. AIs supposedly, it's one of the reasons why I don't understand what their objective is, are trying to emulate human reasoning. But when I look at human reasoning, i.e. at those aspects of reasoning that distinguish humans from other living things, what I find is that there's a lot of things that are shared by all living things. And those things include, learning new knowledge from their environment, the use of pattern recognition and statistical inference, both genetically and individually. There's genetic learning and individual learning. And the ability to manage uncertainty. Those are things that all living things have to do, even plants, let alone animals, or they couldn't survive, their species couldn't survive. But what I observe also is that those are exactly the things that the actual work in AI is trying to achieve. And on the other hand, what humans do that most other species cannot do are create new knowledge by logical entailment, to detect inconsistencies, to use deductive inference, to have primitive operations that do things like abstraction and specialization and generalization and analogy. So I would say that maybe AI has picked the wrong domain, because I don't see anything in AI's practice that is even aiming at the things that distinguish humans. And on the other hand, the things that they are, in fact, pursuing and investing in are the things that are shared by all living things. Okay, how are we on time?
8:10.
Okay. How much time should I take here? I'll just quickly run through this. My own current project now is called PBT Omega, and it's basically an automated logic, but it's a new logic that differs from classic logic and from most other logics that we're familiar with. And its purpose is basically an automated system that will amplify human intelligence. And it emulates or attempts to emulate the logic of human deductive reasoning. By the way, we don't know what the logic of human deductive reasoning is, but we know a lot of its characteristics. There aren't any formal logics, though, that in fact have all those characteristics, at least not before PBT. It's a formal logic effort. It's not an AI effort. It uses deductive and not statistical reasoning, inference in that. And it represents relationships among things, but not things themselves. That is to say, it's analogous to concepts of the mind. Concepts are defined not by their representations, but by how one concept relates to other concepts. Okay, and then the logic itself represents concepts as sets of properties or relationships. The same things we do in human reasoning. Logic is a formal logic. It's sound. It's incomplete. It's devoid of paradoxes. It's intentional. It's monotonic. Well, sound means it can guarantee valid results from valid data. Incomplete means that it can give valid answers in the absence of complete information, which is absolutely necessary if you're going to be able to do deductive reasoning for most domains. It's devoid of paradoxes. A paradox is just an inconsistency that you can't prove within a logic, that is to say. But if you think about it, humans are quite capable of recognizing paradoxes. If I say this sentence is false, you don't have to be a formal logician to say there's something wrong with that sentence. But formal logics, including classic logic, which is the logic we're all taught, and which is the basis for digital computation, cannot deal with that problem. But it cannot recognize a paradox.
Just as a quick housekeeping thing, if you are an IEEE member and are attending this meeting, please type in IEEE in the chat.
Okay, and intentional, it simply means that the logic is able to distinguish between things and representations of those things. We talked about that a bit earlier. And monotonic, I put this down only because AI logics tend to be non-monotonic. And what monotonic means is that if you have a proof, you prove something based on what you know, and then you add new information, it doesn't void that previous proof. And it would be, life as humans would be pretty difficult if every time you got a new piece of information, everything we had previously proven has to be redone. And yet that is the life of AIs. In particular, or at least machine learning. Okay, PBT logic has many of the features of classical logic, but it also has these primitive operations for abstraction, specialization, generalization, analogy that are really the most powerful operations of human reasoning, and yet we don't have them in, not only don't we have them in AI, we don't even have them in classical logic. And finally, because PBT has primitive operations, that same set of primitive operations, but particular abstraction, its proofs can actually be conducted in strictly less than order n squared time, where n is the number of relationships or properties, or whatever word you like to associate with that. And that's significant, because it only with the order n squared or less, I'm sorry, only with less than n squared can you scale computations. Okay, Omega is actually an informal automated language that implements PBT as its underlying logic. And it has, basically Omega has two notations. It has a formal notation, which is unambiguous and looks very much like traditional logic notations. And it also has an ambiguous, informal, natural language-like notation. And it's convenient to use. It's a pain using formal logic notations in general to specify things, but the ambiguity is a price you pay for that. Okay, Omega is a declarative language with computations triggered by questions. So basically, you describe the domain you want to work with. And again, it doesn't require a complete description because it's an incomplete logic, which says that, tell me all you know about your domain, and then ask your question, and that will trigger a computation, which will attempt to answer your question. And because it's an incomplete logic, it says that it'll either answer your question, because it says that is actually, it gives three answers, a choice of three answers. It can say that here's an answer that's entailed by what we know, by what you know and specified, or it's an answer that's consistent with what you know, but not necessarily entailed by it, or it's an answer that is, it's something that's not answerable. Okay, and again, this is a restatement with different words, but incompleteness means things can be vague and imprecise. And that's the way the real world is. We don't have precise measurements of anything in the physical world. And on computers, we often pretend we do, but we don't. And floating point doesn't really help that problem. And we always have incomplete knowledge, which means we want incomplete specifications. We don't want a requirement like we're used to in computers that says, well, we require complete descriptions. Every object must be a complete object. There's no way of failing to completely describe things, either algorithms or representations. And so we're always giving inaccurate descriptions because of the requirement for completeness. Okay, and then I just added this here just to give you maybe a better idea. If you think about natural language, all the nouns, certainly all the improper nouns, describe not individuals, but categories of things. We talk about dogs and mammals and trees and the universe and so on. Those are categories of things, and they're categories that are incompletely characterized by their shared properties. And so in natural language, and by assumption from that, human deductive reasoning really operates on types or concepts that are descriptions of categories in terms of their properties. And again, in natural language, if you look at it, declarative sentences really are assertions that something, the subject, has some property, which is the predicate. And then all the things in natural languages, such as all the modifiers, the adjectives, the adverbs, the prepositional phrases, all those things are properties also. But where in the sentential forms, you're asserting that something has a particular property. When you use it as a modifier, it's saying that you're selecting from the category. As I say, large mammals. Large is a property that is selecting a subset of the category of mammals. And so PBT logic and the Omega language really are just one-to-one with that sort of representation. And I think with that, I'll open for questions.
It looks like you're being sent questions in the chat. So if you look at the bottom bar right next to where the share screen icon is, there should be a chat icon.
Seem to have that at the top, but that's all right.
Ah, okay. Yeah, I'm sorry. When you're presenting, it's at the top, and when you're just viewing, it's towards the bottom.
I see. Okay, so which one should I look at?
There should be an option that says chat.
Yep. Oh yeah, 60 it says. Oh wow. Okay. I take it I want to go to the top of this list. The oldest are at the top.
So there's a question from A. Windsor Brown that is asking, have you or would you consider included causal analysis techniques or tools like tetrad, assuming you have some data about your domain?
That's causal
Not familiar
analysis,
with it.
not casual.
Ah, causal. I'm sorry. Misread it.
I'm sorry, what is it again?
So when you're looking at the presenter view,
Yeah.
there should be, you should see a participants list, and then somewhere near it you should see a chat window or chat.
Yeah, I have the meeting chat window.
Yes.
It's at the bottom.
Yeah, yeah. So it's
Okay, and the last one on here is what was your?
Yeah, but go back to.
Yeah, go back to.
Oh, have you consider using caused analysis techniques? Yeah, I don't see why not. But again, PBT Omega is really a logic system, and so
Well, the whole causal analysis thing is a logic oriented thing, because otherwise you can't
Yes.
prove causality.
Right. I don't see why, as long as you can describe the inference rules for the causal analysis, I don't see that it's a special case.
Tetrad in particular will give you those causal rules.
Right.
With a degree,
I think it's just a matter of importing them.
Pardon? Well, perhaps,
Yeah,
but that's
'cause
the
I know,
point. You have to have it. You have to have some data in a data set sort of orientation, though. Okay, thanks for your answer.
do you keep a record of this chat questions?
Yes, I can email you the chat questions if you're having challenges reading it
Yeah,
from-
because that allows me to get back to some of these people, maybe if I want to talk to them later about their questions. Okay,
Where do we find examples?
yes, a PBT omega to generate new knowledge. Well, understand that for any deductive logic, a proof is really generating new logic. I mean, sorry, new knowledge that is entailed by what you already know. And that's exactly what PBT as a deductive logic does. Where it differs maybe is that it is a logic, because it's an incomplete logic. It does distinguish between, it's not that everything is true or false, or even consistent or inconsistent. There's things that are consistent, and there's things that are inconsistent, and there's things that are not known, or more to the point, not knowable. Well, both, I guess. I don't know if that helps or not. Where can you find examples? I need to make that available somewhere.
Yep.
Particularly because some of the inference rules that are standard in PBT, particularly the set of inference rules that go with abstraction and generalization and analogy, are not ones that we're used to seeing in logics. But no current source.
Oh, how about the tool? Can we get a hold of the tool?
Yeah, I wish.
Oh,
The answer is no, because all the publications I've done so far have been really on the logic. And I do have a new paper that should be out actually this month. Well, I'm sorry, September, on the logic. On Omega, I've done a lot of experimental developments. But we don't have anything to make available. And in fact, we'll actually, I think, probably start from scratch now that we really have the logic in hand. I didn't say it, but PBT really came about as a result of a project from 1984, a DARPA project that I was the PI on, looking at the future of programming languages should be. And what we concluded was that there wasn't much we could do with programming languages in 1984 that hadn't already been done, unless we could come up with a logic that somehow, okay, unless we come up with a logic that, let me get this back. Oh, I bet it's here. Okay. In any case, so we tried to come up with a logic that would meet the requirements, namely a lot of the requirements I showed you for PBT, and we failed at that. That was so 1988, 89, we were finished with that project, but we really didn't have an answer to an adequate logic. And so between then and about 5 years ago, maybe 7 years ago, I've always been kind of working on it in the back of my mind, but it was only in the last really 3 to 5 years that I really came up with an adequate answer. And I knew over all that time that what was critically needed was a logic that could define itself. And we don't have logics that can define themselves. Type systems are able to define, a first order type. A second order type can analyze a first order type, and a third order type can analyze a second order type, and so on. That's a Bertrand-Russell proof, but it's an infinite regression. And so the question is, how can you avoid that and have a language, a logic that can represent and reason about itself? And that's really the key breakthrough that made it work. Okay, other questions? Oh, 3 new messages. Yeah. Okay.
What was your reaction using Chat GPT?
Yeah. It's pretty interesting, let's say. It does. It sounds good. But if you really think about it, if you try to follow its logic, you quickly learn that there isn't any. And I haven't studied it in detail, but I did go to a CMU lecture a couple of weeks ago by 2 faculty that had been studying chat, and that particular chat actually, and they were let's say less than impressed, but on the other hand, they found it useful in some of the work they were doing. So okay, does it surprise me? No, actually it didn't. I mean, although well, yes, I am surprised at how well it sounds, and it really, I think, is kind of the extreme in what you can do with large language models. You really can make things that sound good if you just don't worry about their meaning. Which again is the danger in these things. Okay, you said there was 3 questions here.
Why are all major AI developers
Afraid of
unregulated AI?
I don't know. I mean, I think this idea that AIs are really capable, that they really are going to be smarter than people and take over the world is a real fear that people have. And I think AI developers, I can't imagine they have that fear, because I think they understand how poor and incapable those systems are. But I think they also recognize that if they take any other attitude, that they're probably going to lose their funding. And I have a great fear as well of AI at the present. And the fear that I have is that the general public really does believe that it's capable of things that it's not capable of. And so we see large language models being used for purposes that require meaning and they don't have any. We see autonomous cars, which are fine in non-emergency situations, but I mean, if they're well done, at least they're fine in that situation. But man, you know, I drive an electric car, and I will not have the autonomous features in it. But on the other hand, you know, it doesn't matter what I do with my electric car. If everybody else on the road is using their AIs. And by the way, there's been, I think they said 28 deaths this year so far from autonomous vehicles crashing and killing their drivers or passengers. Yeah, so it's worrisome to me because people will come to depend on capabilities that aren't really valid. And another one here.
How can PBT prevent software from failing?
It won't. I think what it will do is, you know, if you really think about the long-term, since the 1960s software problem, in some sense, a great part of it at least can be attributed to simply the lack of automation in the software development and maintenance process. And I think PBT will go a long ways towards that because it offers the possibility of automatic generation synthesis of programs from specifications of the context and interrogative specification of what problems to be solved. And I have a lot of confidence in that. Like I say, we've done the logic now. We haven't done the an implementation of Omega. But you know, by background, all my life I've been a programming language designer and a person who constructs compilers and designs compilers, and so it's my domain. And I think we know so much about optimization, so much about compiler construction. What happens though is that when you use traditional programming languages, which requires that you overspecify, which doesn't capture the real requirements of the problem that's trying to be solved, the compilers have no way of knowing whether the specifications are real or just there because they had to be there. So I think that the ability to compile is actually going to get a lot better using traditional compilation technologies.
Next.
What is that?
Is the PBT object oriented? Where does AI play a major part? Overloading polymorphs, etc.
Yeah, the answer is none of the above. That is to say, PBT is almost an antithesis to object-oriented. It says nothing is objects are complete things, and PBT Omega says we assume that nothing is completely known, where object-oriented says everything must be completely known. And in fact, if you have something that and almost nothing do you completely know, but if you do, it's not treated as a special case in Omega. It's just something you happen to know everything about. In fact, there's some philosophical issues about whether you actually know everything about anything. Putting that aside. What was the other part there? It was two parts.
Overloading polymorphs, etc.
Yeah, well, okay. This is a real natural language issue. So the answer is yes. PBT is, I would say, has what programming language people call overloading, but it's not, you don't think of it as overloading. And basic, it's analogous to what we have in natural languages. That is to say, the names of things. Remember, everything that's named in PBT Omega is a category. So what happens is that everything from a super category, every property inherits to subcategories. So every property of mammals is also a property of dogs. But it turns out that one of the properties of mammal is that it's called mammal. And therefore dogs can be called mammals too. And so it's a kind of overloading. And that's overloading of types or categories, but the operators are the same way. That operations can be specialized by specializing their formal parameters. That is, taking a subtype of them. And through a proof process that involves abstraction and then specialization, you can also generalize operations to uncover things that were not in the original operator if you can prove that it's not inconsistent with it. But what it says is that unlike overloaded languages, programming languages, there's the meaning doesn't change just because you're using an overloaded version. The meaning is associated with a particular set of properties that are preserved, whether you move up or down the lattice of types, concepts. Okay.
Next one.
What is this one?
That's a big one.
Yeah.
Chat. Do you want me to read it?
Yes, please.
Chat GPT and any large language model using GPT 3.5 or higher knows programming languages. Great at getting the initial 80% done, depends on the prompt, but it does generate code that is deprecated or sometimes incorrect. Any real programmer can figure out those minor issues, but it does accelerate the boring initial 80% of code. This is not hallucinating, just derived from ancient or incomplete input.
Yeah, I guess I believe that. It makes sense. It's not what a PBT system would do, but it's certainly credible using AI and particularly language models. Yeah, I believe that. It reminds me actually of I think it was one of the World's Fairs from the 1960s. Somebody, probably IBM, had a language translation system, natural language translation system. And you walked up to the system and they would have a canned Russian language thing, and you put it in, and almost immediately the English translation would come out. And it was impressive, but it turned out that, of course, that they had actually earlier fed the Russian into the system, and it had produced a translation that was not readable, but it showed what the choices of words were. And then a human went over it and picked out the right word in each case, and then that was put back into the machine, and that's what you saw in the demo. And I think you're talking about something very similar to here with the LLM version of programming. I think it's legitimate. I mean, it's that system that they demonstrated, although they did it in a way that misrepresented its capability. Nevertheless, that sort of translation turned out to be very useful. It's just that you had to have a lot of the hard work, that is to say, the intelligent work done by humans later. But yeah, I would use such a system. Next.
Okay, the next one is a participant giving a link for information on tetrad and causal analysis.
Okay,
So I think
not my thing, yeah.
Next one, would AI destroy itself? Humanity seems to be on a path to self-extinction.
Yeah, well, I don't know about the humanity being on a path to self-extinction. It's certainly possible. There's a lot of evidence of that, but on the other hand, I suspect it will not happen.
Would AI destroy itself?
Yeah, and see, again, this reminds me of things that have happened in the past. You know, in the 1960s, there was this what we saw with the exponential increases in the capabilities of computer hardware that increased the expectations. I had a slide on that earlier for software, and so the demands on software were going up and up and up, and the quality of software developments and things was going down and down. And it was just clear that, you know, this all programs are buggy and you can't fix it, was the character of the world. And we said, this is just going to lead to what we call the coming software crisis. And we had a list of all the characteristics that software would have in the presence of this crisis. And, you know, 10 years later, everything on that list was true. And there was no crisis. People just accepted that as the norm and went on. And, you know, as you know, we accept that programs are buggy, and that's the way it is. And it's kind of sad, but it's, you know, I think crises tend not to occur in the real world because people find ways of dealing with them one way or another. Will AI kill itself? Well, the answer is, to the extent that it's useful or helpful, we'll probably keep AIs around for a long time. Although again, I have to go back and say how many new well, I had in my talk, I probably gave 20 different AI technologies. You know, how many of them are currently being used to do no software developments? And the answer is very few, because they've proven that they are not cost effective. And I think that's going to happen with the large language models. And they see there's the problem with the large language models. They're super expensive. And so, you know, the ones we've put big money into, we can continue to use, but we're probably not going to put big money into new ones once we discover that, you know, language requires not only sounding nice, but having meaning as well. Okay.
So I think that's going to be our final question for tonight.
Unfortunately.
Oh, okay.
So that's going to be our final question for tonight, I think. Thank you everyone for attending tonight. Thank you, Mr. Fisher, for your presentation. I think all of us thoroughly enjoyed it. For those of you that stayed all the way to the end, there are additional sessions going on. There's actually, I believe, 3 more sessions, one on the 10th the 17th and the 31st. If you have any questions, you can send an email to Mr. Fisher at via his email dafisher@ieee.org. Again, thank you for
anybody has any comments or interest in collaborating on something related to the things I'm doing, send me a line.
All right. Well, I think that concludes our presentation for tonight. Have a great rest of the night, everyone.
Thank you.